Ever wondered how common drugs like ibuprofen and propranolol are synthesized? Let's take a moment to appreciate the art and science behind these everyday miracles. Today, we're going to peel back the layers of complexity and reveal the magic behind the synthesis of 4 common drugs: ibuprofen, propranolol, ciprofloxacin, and sulfamethoxazole. Each of these drugs has a unique story to tell, a journey from the lab to the pharmacy shelf. Understanding their synthesis is not just a fascinating journey into the world of chemistry, but also an essential step in the development of new, more effective treatments. So, why is this important? Simple. By understanding the synthesis of these drugs, we can better comprehend their mechanisms, their potential side effects, and how they can be improved. Ready to dive into the world of drug synthesis? Stay tuned. Ibuprofen, a common pain reliever, has a more complex creation process than you might think. Let's take a deep dive into the fascinating world of chemistry and understand the retrosynthesis process of ibuprofen. The journey begins with the end product, which is the ibuprofen molecule, and we trace our way back to the simpler compounds from which it's derived. Imagine the ibuprofen molecule as a complex jigsaw puzzle. We start by dismantling it into its key pieces. The first step involves breaking down the ibuprofen molecule into 2 main components, a carboxylic acid and an isobutyl benzene. This process is similar to unboxing a puzzle and identifying the corner pieces. Next, we look at the carboxylic acid component. It's derived from a simple compound known as propionic acid, which undergoes a series of reactions to become a more complex structure. These reactions involve the addition of a chemical group known as the acyl group, followed by a reduction process. On the other side, the isobutyl benzene is derived from a process called Friedel-Crafts alkylation. Here, benzene reacts with an alkyl halide in the presence of a Lewis acid catalyst. The reaction results in the addition of an isobutyl group to the benzene ring. Finally, we reach the last step of the retrosynthesis, combining these 2 components. This is done through a process known as Fischer esterification, where the carboxylic acid and the isobutyl benzene are heated together in the presence of an acid catalyst. The result? Our familiar friend ibuprofen. Just like a completed jigsaw puzzle, every piece fits perfectly to form the final product. It's fascinating to think about the intricate processes that go into creating something as common as a pain reliever. So next time you reach for that little tablet of ibuprofen, remember the journey it's been on. From simple compounds to a complex molecule, it's a testament to the beauty of chemistry and the ingenuity of scientists. And that's how a simple tablet of ibuprofen comes to life. Next on the list is propranolol, a beta blocker used to treat heart conditions. This remarkable compound is a workhorse in the field of medicine, but have you ever wondered about its origin? Let's delve into the retrosynthesis of propranolol and shed some light on this process. Imagine propranolol as a puzzle. Our task is to disassemble it into simpler pieces. These pieces are the building blocks of the molecule, and the process of breaking it down is what we refer to as retrosynthesis. Propranolol is made up of 2 key fragments, the naphthyl and the isopropylamino fragments. The synthesis of the naphthyl fragment begins with a simple naphthalene molecule. Through a series of reactions including nitration, reduction, and Friedel-Crafts acylation, we end up with the naphthyl fragment. On the other hand, the isopropylamino fragment is synthesized from isopropanol. This undergoes amination, followed by reduction to give us the desired isopropylamino fragment. Once we have these 2 fragments, the next step is coupling them together. This is achieved through a nucleophilic aromatic substitution reaction. The isopropylamino fragment acts as a nucleophile and attacks the naphthyl fragment, pushing it to form a new bond and creating our target molecule, propranolol. But it's not over yet. The newly formed propranolol still has a nitro group attached, which isn't part of the final structure. So, a final reduction step is needed to convert this nitro group into an amine, completing the synthesis of propranolol. As you can see, the retrosynthesis of propranolol is a complex dance of chemistry, requiring careful orchestration of reactions and transformations. It's a testament to the ingenuity of scientists who have mastered the art of molecular manipulation, turning simple building blocks into life-saving medicines. Isn't it fascinating how these compounds are synthesized? It's like watching a magic show where the magician is a chemist and the magic is the transformation of simple compounds into complex, life-saving drugs. But remember, this magic is grounded in hard science, and it's a science that continues to evolve and advance, just like the world around us. Now let's turn our attention to two popular antibiotics, Ciprofloxacin and Sulfamethoxazole. First, we'll tackle Ciprofloxacin, a fluoroquinolone antibiotic that's a heavyweight in the battle against bacterial infections. Its molecular structure is a bit complex, but don't worry, we'll break it down step by step. The retrosynthesis of ciprofloxacin commences by splitting the molecule into three main fragments. These are piperazine, cyclopropylamine, and a highly functionalized aromatic compound. The challenge here lies in the formation of the quinolone core, which is a fusion of two aromatic rings. The key reaction in the synthesis of ciprofloxacin is the cyclization of the aromatic compound to form this quinolone core. This reaction involves the use of a strong base to ensure the elimination of a leaving group, followed by an intramolecular cyclization. The resulting compound then undergoes a series of reactions, including halogenation and amination, to yield the final product, ciprofloxacin. Next, let's move on to sulfamethoxazole, a member of the sulfonamide antibiotic family. Its structure is simpler than that of ciprofloxacin, but its synthesis is no less fascinating. Sulfamethoxazole can be retrosynthetically broken down into two main fragments, an aromatic amine and a sulfonamide. The key reaction in the synthesis of sulfamethoxazole is the formation of the sulfonamide bond. The synthesis begins with the nitration of aniline to form a nitroaniline. This compound is then reduced to yield our aromatic amine fragment. Simultaneously, the sulfonamide fragment is prepared by reacting sulfuric acid with ammonia. The final step in the synthesis of sulfamethoxazole is the coupling of the aromatic amine and the sulfonamide. This reaction is typically carried out in the presence of a strong base to facilitate the formation of the sulfonamide bond. So in summary, the synthesis of these two antibiotics involves a series of intricate reactions and intermediates. For ciprofloxacin, it's the quinolone core formation that takes center stage, while for sulfamethoxazole, it's the formation of the sulfonamide bond. It's quite impressive, isn't it? How these complex molecules are meticulously assembled in the lab, step by step, to create powerful antibiotics that help us fight off infections. And that's what makes the field of drug synthesis so fascinating. So that's the story behind these two powerful antibiotics. In today's video, we've uncovered the fascinating processes behind the synthesis of 4 common drugs. The magic that happens in the laboratories, the intricate dance of molecules, and the pioneering spirit of the chemists who make it all possible. Let's take a moment to appreciate the complexity of what we've learned. Ibuprofen, a common name in many households, starts its journey as a simple molecule of isobutylbenzene. Through a series of chemical reactions, it transforms into the anti-inflammatory powerhouse we know and rely on when we need pain relief. Then we have Propranolol, a beta blocker that helps keep our hearts beating steadily. Its synthesis involves a delicate balance of reactions, starting with the humble naphthalene molecule. The way it transforms into a life-saving drug is nothing short of a marvel of modern chemistry. And let's not forget about ciprofloxacin and sulfamethoxazole, antibiotics that have saved countless lives from the scourge of bacterial infections. Their synthesis journeys are equally impressive, starting from basic organic compounds and ending up as potent weapons in our battle against disease. These aren't just chemical reactions happening in a test tube. They are stories of innovation, perseverance, and ingenuity. Each step in the synthesis process is a testament to the tireless efforts of scientists who've dedicated their lives to enhancing our health and well-being. But why is understanding drug synthesis so important? It's not just about appreciating the science behind the pills we take. It's about understanding the effort, the trials, the failures, and the triumphs that go into each tablet. It's about recognizing the crucial role of pharmaceutical chemistry in our lives. So next time you reach for that bottle of ibuprofen or propranolol, remember the journey it has taken to reach you, the intricate dance of molecules, the complex reactions, and the brilliant minds that made it all possible. Remember, every tablet you take has a story behind it, a story of chemistry, innovation, and hard work. Subscribe for more because you won't find me later.